Okay, hello guys again. How are you doing? Today I'm gonna be solving some problems. Chapter 2 and Chapter 3. The first one is from Chapter 2, and basically it's something that I didn't mention during the last session. It's about dot product. So we're gonna be solving this problem here, and let's start by looking at the problem and what the problem is asking us to do. It says determine the angle phi between cable AC and the strut AO. Let's identify this. We say the angle phi between AC is this one here, and AO is this one here, and of course the angle that we are looking for is going to be this angle here, that angle phi. That was the first part of the problem, and the second part of the problem asks for determine the projected component of that force AC, which is this tension, and the magnitude is 60 pounds, along the strut AO, and express the result as a Cartesian vector. So we have to do two things. We have to determine the projected component in magnitude and also the force as Cartesian vector. Okay, let's start with the first part. Let's try to work out the first part. And when the problem asks for determine the angle between phi the angle phi between the cable AC and the strut AO, immediately when you see this problem is telling you to do dot product or apply the definition for dot product. If you remember dot product, there are several things that we have to remember. First of all, the definition of dot product, if you have two vectors, whatever the two vectors are, in this case the two vectors are AO and AC, and this is the angle phi that is between the two vectors. The definition of the dot product says that the vector AC dot the vector AO has to be equal to the magnitude of the vector AC times the magnitude of the vector AO multiplied by the cosine between the two vectors. And be careful with that, because it's exactly in the way that we are showing here. The two tails have to be together when you do the dot product. That means that the vector that we are looking for is AO in this direction, and the other vector is going to be the force AC. Why I'm saying that? Because if by any chance you calculate the vector in the other direction, the OA instead of AO, basically the angle that you're calculating is this and not this, the supplementary angle. So be very careful with that. Both tails has to be together when you apply dot product. So the first thing that we're going to do for solving this problem is what? Well, we need the dot product. In order to do the dot product, we need to express the vectors in Cartesian formulation and Cartesian notation. So find the components I, j, k of each one of the vectors, and then we have to find the magnitude of each one of the vectors. Let's start with the vector AC. For the vector AC, I have to find the vector. And how do I find the vector for that particular force? Well, there are several ways, but in this case, as you can see, you have basically the coordinates of the point. You don't have the coordinates per se, but you have all the distances that you can use for calculating the coordinates. And so that means that you can calculate the position vector AC, and that position vector AC can be used later for if you want to decompose the force. For decomposing the force, we really don't need the unit vector in the direction AC, because what we are calculating only is the angle, not the force in Cartesian notation. So let's start with the coordinates for this point. The coordinates for the point C here. The coordinates for the point C are, in X, it's going to be this one. Let me draw it here in this blue color. So that point C is going to be here. So you have the X coordinate and the Y coordinate here. The X coordinate in this direction is going to be 5, cosine 60 in this direction, which is I. Well, this is not I, this is just X because it's just coordinates. So 5 cosine 60, and as you can see, it's over the plane XZ. So the coordinate J is 0, and the coordinate in Z, which is this one, is going to be 5 sine, because it's the opposite, sine 60 degrees. I'm going to express this coordinate now as 5 cosine 60, which is 0.5. So basically this is going to be 2.5, 0. And this is the square root over 3 over 2 multiplied by 5, which is 4.33. And we have the coordinates of the point C. The coordinates of the point O, I'm going to need it for later, but they are 0, 0, 0, because we established our origin in that point. And the coordinates of the point A are, the point A, it looks like it is over the, exactly on top of the, over the axis Y, but not on top of the axis, right? Over the plane, let's say that is over the plane ZY, that point. So the coordinates of the point A are going to be 0 in X. In Y you have this distance, which is 6, and 2 meters in the Z direction. That's basically it. Okay, let's start with the position vector AC. The position vector AC, remember, has to be obtained by subtracting the coordinates of C minus the coordinates of A, and that's the most common error when people work with vectors and coordinates. Remember, it's always tip minus tail. So 2.5, 0, 4.33, those are the coordinates of that point, minus 0, 6, and 2, which give us the vector AC as, now expressed as a vector. 2.5 minus 0 is 2.5 I. 0 minus 6 is going to be minus 6J. And 433 minus 2 is going to be 2.33K. And we have the vector AC. I'm going to box it, even though this is just a partial result. It's not what we're looking for, but I like to keep my answers in a box so I can find them easily. Now we need AO, the vector AO again. The vector AO is from here to here, and remember, then you have to subtract coordinates of O minus coordinates of A. So it's 0, 0, 0 minus these coordinates, which are 0, 6, 2, which give us the vector AO as 0 minus 0 is 0, 0 minus 6 is negative 6J, and 0 minus 2 is negative 2K. I know that I'm going to need the magnitude of AC and the magnitude of AO because they are here. So if I want the magnitude of AC, the magnitude of AC is going to be the square root of the summation of the elements squared, 2.5 squared plus 6 squared plus 2.33 squared, which give us a magnitude for AC equal to 6.905. Even though these are just partial results, don't lose perspective of what you are working and what we are dealing with. This is a distance, so my distances are in feet. This is going to be feet. Same thing with this. This is a vector, but the magnitude should be, or the unit should be feet for that vector. Now, for the vector AO, same thing. The magnitude of the vector AO is square root of 6 squared plus 2 squared, which is a square root of 40, which gives us the magnitude for AO of 6.32 feet. Now the only thing that we have to do is apply our equation for dot product. We have to to get the multiplication of AC dot AO. We have AC and we have AO. If we dot multiply this, it's going to be I with I. Remember, this is 0 I here. So I with I is 0 plus J dot J, that's 36. Let's calculate that part first. AC, not the magnitude, as a vector, dot AO is going to be equal to 2.5 I minus 6J plus 2.33K multiply or dot multiply by 0 I minus 6J minus 2K. And when you do that, we're going to have then 2.5 times 0 is 0, and 6 times 6 is 36, positive 36, and 2.33 times negative 2 is negative 4.66, and this value is going to be 31.34. And remember, the units for the dot product are going to be the same units of each one of the elements multiply. So this is fit, this is fit, this is going to be fit square. So we have this part, and we have the magnitude, and we have the other magnitude. Then I can solve for cosine phi, which is going to be the value that we got for AC dot AO divided by the magnitude of AC multiplied by the magnitude of AO. In other words, it's going to be 31.34 divided by the magnitude of AC is 6.905 multiplied by 6.32. And this value comes to be 0.718, which means that our phi angle is going to be the inverse cosine of 0.718, which gives us a phi of 44.1 degree. There you go. We have already the first part done. Now the second part. For the second part of this problem, let me get a new piece of paper. For the second part of this problem, it says determine the projected component of the force AC. And if you remember, once again, the definition for dot product basically is the projection. Dot product gives us the projection of one vector over other vector. So if I want to find the projected component of AC over AO, what I have to do is dot multiply. Let's call this in this way. The projection of the force AC over the vector AO, I'm going to call it like that, it's going to be just the dot multiplication of the force AC times the unit vector in the direction of AO. That's what is going to give us that projection. Do I have the force AC? No. Do I have the unit vector AO? No. But I can have it really easy, because the force AC is going to be just the magnitude of the force AC, which I have, is 60, multiplied by the unit vector in the direction of AC, which is no other thing than the vector AC divided by the magnitude of the vector AC. And I have both of them. So this is really easy to do, because I have this value is 60 multiplied by AC, and AC is 2.5 I minus 6J plus 2.33K divided by the magnitude of this, which is 6.905 if I'm not mistaken. Yes, that's what we calculated before. You see, this is the AC and this is the magnitude, 6.905. That's going to give us the force AC. And the unit vector the unit vector AO is going to be whatever is the value of AO that we calculated before also. AO is here, negative 6J, negative 2.5K, .5 2 negative 6J negative 2K divided by the magnitude of AO, which is 6.32. So basically what I have to do now is just dot multiply this and that. And when you dot multiply this times that, I could solve it partially, but I don't want to. If I do this now, FAC dot multiply by the unit vector in the direction AO, I can do it just by getting this 60 here divided by 6.905 and this divided by 6.32 also here, and then I'm gonna do the multiplication, dot multiplication of the two vectors, which is gonna be 2.5i minus 6j plus 2.33k dot multiplied by negative 6k, negative 2k, negative 6j, I'm sorry, negative 2k. But I did this before. When exactly I did that? I did that here. I did that multiplication before, which is 31.34. So I don't have to repeat that value. This multiplication is 31.34. But it's another thing that, 6 times 6, which is 36, and negative 4.66, and that's 31.34. And when you multiply that, you can get that the force AC projected, or the magnitude of the force AC projected over the strut AO is equal to 43.09, and the units are pounds because those are the units that we're working with. But this is just part of the solution because the problem is asking us to calculate also the direction. Well, what is the big deal? I multiply this by the unit vector in the direction of AO, which is this one, and then I have the force in vector notation. So if I want the force, not just the component of the force acting over AO, the magnitude, but the force, the real force, AC with direction acting over AO, is going to be the magnitude of that force multiplied by the unit vector in the direction of AO. So I multiply that by negative 6j, negative 2k, divided by 6.32. You can simplify this if you want to put some numbers, but I don't like working partial results. And this is going to be equal to negative 40.9j, negative 13.64k. So this will be the projection of the force AC over the strut AC over the strut AO, this strut here, as a vector and in magnitude. Now look at this. This particular part of the problem could be done differently. How come? Because if I apply once again the definition of dot product, and I can say that the definition of dot product is this one, I can say that FAC dot multiply by the unit vector in the direction of AO, that's going to be equal to what? To the magnitude of AC multiplied by the magnitude of this unit vector. What is the magnitude of the unit vector? 1. Multiplied by the cosine of the angle between both of them. And it happens that I calculated before that angle, which is 44.1. And also I have the magnitude of AC. So if I wanted to calculate that projection, I could say that it's 60 cosine of phi, and phi is 44.1 degree. And this is going to give us 43.09 pounds, which is the same value that I calculated before. When you do this, when you do the other one, it's depending on the problem, depending what intermediate step you have to calculate for what situations. But basically, you have the two solutions for this problem here. And that problem is a really nice problem involving dot product. You can go and redo it in your book. There are a lot of problems similar to this, and even more complex and easier also than this one. Okay, that's the first problem. Let's do the second problem now. Now the second problem that I'm going to solve is linked to chapter 3. Now chapter 3, we have this problem here. Remember, chapter 3 starts dealing with equilibrium in 2D, particle equilibrium in 2D. It says determine the tension developed in each core required for equilibrium. This is the key word here. Equilibrium of the 20 kilogram lamp. So that lamp has a weight of 20 kilogram. No. That lamp has a mass of 20 kilogram. Meaning that the weight is going to be 20 times 9.81. And that's 196.2 newtons. Kilogram, meter, second square, Newton. Okay, so basically I know this here. Particle equilibrium, I have to determine the tension in each one of the cores. I have to develop the tension in this core, this core, this core, this core, and this core. But this core, I already know it. Because if I do a free body diagram of that particle F, if this is the particle F, and I do a free body diagram, I'm going to have the weight, 196.2, and I'm going to have this chord, dF or FD. And if I do summation of forces in Y here, I can get directly that dF equal 196.2 Newton. Now, remember, when we are dealing with particle equilibrium, we are dealing basically with two dimensions, and a particle can move only in two ways, in two dimensions. So we have two possibilities for movement. That means that we have two possible equations also. Our equations can be summation of forces in whatever two directions you want to, but it's easier to work with X and Y in most of the cases. So that's what we're going to do. If we have two possible equations, the maximum number of unknowns that we can have is also 2. By unknowns, I mean unknown forces in this case. So then I'm going to go to particle D, and I'm going to see particle D. Particle D is here. And this is not a pulley, this is a ring. If it was a frictionless pulley, we have to remember the tensions through a frictionless pulley are the same or are considered to be the same, but this is a ring. So we have three really distinct forces here. We have the force DC or CD. We have the force DE or ED. And we have this other force which we already know, and it's 196.2. I'm not going to put the units every single time, but from time to time, remember to put the units. So this angle here also, we know it, and it's 30 degrees. There you go, one unknown, two unknowns. That means that we can solve this problem because we have two equations. One thing that I always say, when you do the free body diagram, remember you have to isolate this part and put every single force that is there, acting and reacting. Now, why do you put this force pointing up? Because it could come down. Why? Because these are cables, and cables don't push. Cables always pull. So the cable either is zero the tension or it pulls. That's why I put the forces going up. If those, instead of being cables, were rods, let's say steel rods or pipes, the direction of these forces could be different, but it doesn't matter, because once we go further into the program, you're going to see that I could assume the direction going down, for example, going in, but the result when I get it is going to be negative, and that's going to tell me that I mess up with the assumption, basically. But in the case of cables, you always put the cables in tension, because it's the only thing they can do. Okay, here you have two possibilities also, summation of forces in X and summation of forces in Y. You can start with whatever you want to, but the easiest way for not wasting time is to start with summation of forces in Y. Reason for that, if I do summation of forces in X, I have this unknown and the horizontal component of this, which is also one unknown. But if I do it in Y, like I'm going to do it now, summation of forces in Y equals 0, then I have the vertical component of dE is going to be dE sine of 30 degrees, because I'm looking for this component, right? Vertical, dE opposite sine of 30 degrees, positive because it's pointing up, and I'm assuming, I didn't say it, but I am assuming these are my axes here. So it's pointing up, axes go here all the time, and minus 196.2 equals 0, and dE is going to be equal then to this multiplied by 2 basically, which is 392.4 Newton. Once I have that, I can come back and say summation of forces in X equals 0, and if I do summation of forces in X equals 0, I have this force DC negative. Why negative? Because it's going to the left, and I'm assuming positive is to the right. So negative dC plus the horizontal component of dE, which is adjacent to the 30-degree angle. That means that it's going to be cosine dE cosine 30 degrees, and that's it, equals 0. But dE I just calculated, and it's 392.4. So then I can solve for dC. I plug this into here, multiply cosine 30, pass to the other side this term, and dC is going to be positive, and it's going to be 339.83 Newton. And we are done. No, we are not. We are not done. Because it says each chord, so that means that I need the chord AC and the chord CB or BC. Well, there's no big deal with that. I go to the joint C now, or to the point C, the particle C. This is my C particle here. And then I'm going to have this force, which is the force CD, which is in tension, and it's 339.83. And then I have this other force here, which is the force AC, and this other force here, which is the force BC, and this angle is 45 degrees. And remember, this little triangle there is given. You can calculate the angle here if you want to, but you don't need to, because you have the ratios that you're going to need for these components. So let's start. In this case, I have either in X or Y, I'm going to have two unknowns. So I'm going to start with summation of forces in X equals 0. And then starting with the force AC here and here. In X, I'm going to have this component, X. And this component, I can say that 3 is to 5 is 3/5 of AC. And it's negative because it's going to the left. And the component to the left, the horizontal component of this force is this, right? Or is this, the same thing here. And this angle is 45, the same angle. So it's going to be minus BC cosine, because it's adjacent, cosine 45 degree, plus this other one, equals 0. That's for X. Now for Y, then we're going to have the vertical component of AC. Let's do summation of forces in Y equals 0. Then my Y component here is going to be 4 divided by 5 AC, and it's positive because it's pointing up. And the vertical component of this one, this angle is 45, or this one is the same distance, the same magnitude. So this force here is going to be negative because it's going down. BC sine 45, and there's nothing else, so that's going to be equal to 0. And then we solve this system. The way you solve that system is up to you. I always tell you to look for the system, watch a little bit, and try to solve it. But you know something, if you realize this here, if I multiply this whole equation by -1, this is going to be negative now, and this is going to be positive here if I multiply by -1. And what happened is that BC cosine and BC sine have the same value, and this term are going to cancel out. Then you have -3/5 plus 4/5 is -7/5 of AC equal a -33.9.3. If I pass this to the other side here, negative sign cancel out, and AC is going to be 339.3 multiplied by 5 divided by 7, which gives us a value of AC. I have it somewhere. 242.73 Newton. And after we have this value for AC, I can plug it into here if I want to, and solve for BC, and then we get the value of BC equal to 275 Newton. And now we have DF, DE, DC, AC, and BC, which are the tension in all the chords, and that's what we were asked in this problem. That's an easy problem, but that problem is representative of what particle equilibrium is. Okay, I have one more problem. And this problem has proven to be a pain and a headache for students during long time. And the reason for that is because students try to solve without even thinking what they have to do. And that's the problem. Let's start from the beginning and let's see what happened here. It says the cable ABC has a length of 5 meters. We have to, the first assumption that we have to have here is that cable ABC is an extensible. It's not going to deform. It will be different if they say that this is an extensible cable and they give us a value for K, because then the length is going to change as this is dropping. But in this case, the stiffness is infinite. It doesn't say it, but we have to assume that. Now, it says determine the position x, this distance x, and the tension developed in ABC required for equilibrium of this 100 kilogram sac. All the time, when you see that, immediately 100 times 9.81 if we are dealing with SI units, or 62.4 if we're dealing with USCS units. So this is going to be 981 Newton. That's that way. Now, we are missing, or looks like we are missing, pieces of information, because if I have this angle and this angle, that will help a little bit the solution of the problem, but I don't have them. Or do I? Or do I know a relation between those angles? I don't know. I have distances everywhere, this distance, and I have not a clue what I'm going to do. Well, let's check and let's study this. First of all, it says that neglect the size of the pulley. When you read that, immediately, that's frictionless. That's what it means. Frictionless pulley. And frictionless pulley means that the tension BA is going to be the same tension BC. So I have a piece of information. I have the tension here, and I have the tension here. And this, I'm going to call it T, because I say that TAB is equal to TBC, and that's equal to T because it's frictionless. And I have this weight here of 981 Newton. Now, I could even know the magnitude of this already, but I'm going to take it easier. So let's keep working. Now, why am I doing this? Because in case I'm not very savvy doing these problems, and I don't have the sufficient practice, I have to prove everything because my assumptions might or may not be correct. So I'm going to call this angle alpha, and I'm going to call this angle here beta, and I'm going to do summation of forces in x equals 0. So if I do that, then I'm going to have negative t cosine alpha plus t cosine beta has to be 0. Now if I divide by t, this t and this t cancel out, and I pass this to the other side, then I have that cosine alpha equal cosine beta, and that only happens if alpha equal beta. So instead of saying alpha and beta, now I'm going to say alpha and alpha. These two angles are the same, and that is a really crucial piece of information for me. Now, what else can I get from here? Well, I could get the vertical component if I want to, in function of the angle, but it still doesn't tell me anything. So let's go back and let's see what the problem is asking us to do once again. It says the position x. What do I know? I know the total length is 5. Well, I'm going to divide that total length in two lengths, in this length and in this length. And this length I'm going to call it L1, and this length I'm going to call it L2. So I have a first equation, if you will, which tells me that L1 plus L2 equal 5. Now that I know these angles are alpha, and this angle is alpha, I could complete the triangle, let's say here, and say this distance is x, and this distance is 3.5 minus x. 3.5 minus x, so this distance is going to be 3.5 minus x. And why I'm doing that? Because I could express L1 in function of alpha and in function of x. How come? How is that? Well, I can say that cosine alpha is equal to x divided by L1, or L1 equal to x divided by cosine alpha. And at the same time, if I do the same thing here from the other side, I can say that cosine alpha is equal to 3.5 minus x divided by L2, or I can say that L2 equal 3.5 minus x divided by cosine alpha. And guess what? I have L1 and I have L2. I'm going to plug these two into equation 1. And if I plug these two into equation 1, I'm going to get x divided by cosine alpha plus, this is L1, 3.5 minus x divided by cosine alpha, and this is L2, equal 5. This cosine, I'm going to pass it to the other side, multiplying. So then I'm going to have the numerator here as x plus 3.5 minus x equal 5 times cosine alpha. And look what happened almost miraculously with this x here and this x here cancel out. And then I take this 5, pass it divided to this side, and then I say cosine alpha equal 3.5 divided by 5, which alpha is going to be the inverse cosine of 0.7, and alpha is going to be equal to 45.47 degrees. Once you have that, my friends, basically the problem is solved. Because if I want to calculate the tension here, I could just do summation of forces in y equals 0 in this part for calculating the tension now. I can come here and say summation of forces in y equals 0, and then I have t sine alpha plus t sine alpha, which is 2t sine alpha, because t sine alpha plus t sine alpha is the same, minus 981 equals 0. Alpha is 45.47, so t is going to be equal to 981 divided by 2 times sine 45.47, and t is going to be equal to 686.87 Newton. And that's the problem. No, it's not. Because, yes, we did the tension, but we haven't calculated this position x. Now, how you calculate that position x is a little bit more of trigonometry than anything else. But we can solve it. Let me get a piece of paper here. Yes, piece of paper. What I'm going to do is I'm going to work with this shape. I'm going to have this here, this here. I know this is 3.5 minus x. I know this is x. I know this is 0.75, this height here. I also know the total distance L1, L2 here, and I know my angles. Yes, I know the angles. I don't know if I need the angles, but I know the angles. So now I have to calculate this x and this 3.5 minus x. The only thing that I know, this angle is alpha, and if this angle is alpha, this angle is alpha here. And at the same time, I also know this angle is alpha, which means this angle is alpha here also. Let me call this distance that I don't know y. Well, if I use this small triangle and I say tangent alpha is going to be y divided by x. And if I use this big triangle and I say tangent alpha is going to be this height, which is y plus 0.75 divided by 3.5 minus x. But I know how much is tangent alpha because I know the angle. I calculated the angle. So basically the problem is solved, if you wish. I just take this 3.5 minus x, pass it to this side here, and this x tangent alpha, pass it to that side also over there. And I can establish a system of two equations with two unknowns if you want to. Or you can say, I don't know, you can say that in the first equation x tangent alpha equal y, and the second equation 3.5 minus x tangent alpha equal that. Or you can get this x here and say y equal x tangent alpha and plug it into here. It's up to you. I don't know. I can pass this to this side now. 3.5 minus x tangent alpha and equal to y, but y is x tangent alpha plus 0.75. I can do that. And now when I multiply these, I'm going to have 3.5 tangent alpha minus x tangent alpha equal x tangent alpha plus 0.75. And then if I pass these to that side, and this to this side, I'm going to get 3.5 tangent alpha minus 0.75 equal, I pass this to that side, it's the same value, it's going to be 2 tangent alpha x. Divide this here, x equals 3.5 tangent alpha minus 0.75 divided by 2 times tangent alpha. And then I can solve this. This divided by this is 1. 3.5 divided by 2 is 1.75 minus this divided by this, and you can calculate the value for x. And x is going to be 1.38 meters. But this is more like a geometric problem, and you can solve it in any way that you really wish, or you know, or you can. The two basic assumptions, which are not assumptions, that you have to do basically is the first, the cable is inextensible, and second, the angles are the same, and you have to know that they are the same. Or you have to prove them if you don't know them. Okay, we have 3 problems so far, but I have more. I had one of the nightmares of the students. Students have nightmares with these type of problems when they start looking at springs everywhere. And I don't know why they fear about that. They fear the strings. They fear the strings, as they fear a lot of things in life. But if you know what fear means, it's false expectations appearing real. There's nothing. Why are you going to be scared of a spring? Then don't look at the spring. Those are forces. In this class, every time that you see a spring, be happy that everything is going to be working in the elastic range. And when you see a spring and you see a constant, forget about the spring and constant. Those are forces. Determine the stretch in springs AC and AB. What they are asking us to calculate is determine the forces in those cables. What do I know? Equilibrium 2 kilograms. What did I tell you? 2 kilograms times 9.81. That's automatic. And that's going to be equal to whatever it is. This is 19.62. So basically what I have to do is particle equilibrium at A. That's the fear that you have with that problem. Look at that. Particle A. Force AB. Force AC. And 2 times 9.81. Do you know the angles? Well, this is 3 and this is 3. 45. Do you know this angle? Well, I can calculate it if I want to, but instead of calculating, I can say this is 4, this is 3, and this is 5. How do I know it's 5? Because 3, 4, 5, that's a typical triangle. And if you don't know it, this is going to be the square root of 16 plus 9. 4 squared plus 3 squared, which is the square root of 25, which is 5. So basically you have that. What do you do now? Summation of forces in X, same thing, equals 0. Same thing, once and again and again. In X, what do you have in X? Negative AC cosine 45. Why negative? Because it's going in this direction, and the component that you have is this one, right? And this one. And in the other case, you have this one and this one. So it's going to be negative AC cosine 45. And how much is this one? It's going to be positive because it points to the right, and it's going to be 4/5. 4/5 AB equals 0. Now you do summation of forces in Y equals 0. What do you have in Y? Well, you have this one here, which is positive, AC sine 45, because now it's the opposite angle, plus this one, but this one is 3/5 AB, minus 2 times 9.81, which is 19.62, equals 0. What do you do now? Whatever you want to, but sine and cosine of 45 are the same. Negative AC, positive AC. I add the equations, these two. And now I have 4/5 plus 3/5 is 7/5 AB equal, pass this to the other side, 19.62. AB is going to be equal to 19.62 times 5 divided by 7. and AB is going to be equal to 14.01 units Newton. That's the tension AB. I get this value and plug it into either here or here. The first one is easier. If you call this 1 and this 2, plug it in 1, and then you have negative AC cosine 45 plus 4/5 multiplied by AB, but AB is 14.01, which give us AC equal 15.86 Newton. Is that the result? No, but the result is there, because what we are asked to do is calculate the stretch in the springs, and we have the constant. So basically what we are going to say now is the tension AC is going to be equal to the K AC multiplied by the stretching AC. So the stretching AC is going to be the tension AC divided by K AC. Tension AC 15.86 divided by KAC 20, and that's going to give us the stretching for AC is going to be 0.793 meters, or you can express it in millimeters or in centimeters if you want to. And similarly, the stretching of AB is going to be equal to the tension AB 14.01 divided by the K, which is 30. And remember, these units here for the force are Newton, and this is Newton divided by meter. That's why we are getting the results that we are getting in meters. And the stretching of AB is going to be equal to 0.467 meter. There you go. That's your fear spring. And I think we can do one more. So let's do one more. And once again, don't get used to this, because I don't know if I'm going to be able to do it for every single class. Okay, the popular antenna. Why I say the popular antenna? Because everyone that knows me is going to tell you, oh, study the antennas because that's going to be in the test. Maybe not. But I like the concept because it's a 3D problem, and you have to work with all the forces. The cable AD is tightened, this cable here, with a turnbuckle and develops a tension of 1300 Newton. First thing that you know, cable AD here in this direction has a tension of 1300 pounds. Let's say Newton, I think. Determine the tension developed in the cables AB and AC, and the force developed along the antenna tower at the point A. I'm going to put it pointing up. I could choose if I wanted to make it pointing down, because I don't know exactly what force they are asking me. I'm assuming that the force that they are asking me is the force that the antenna is applying to the cable. So that's why I'm putting it going up. It's going to change the direction. Yes, it's going to change the result, but it's going to change only the magnitude of that result. The magnitude, no. The direction of the result. So that's basically what we have. How are we going to do this problem? Well, we're going to decompose each one of the forces, decompose or express each one of the forces in Cartesian. That's what we're going to do. And then apply the system of equations. I mean, summation of a scalar equation in X, in Y, and in Z has to be 0. Or you can say summation of forces as a vector has to be 0, but at the end is the same thing. Or you can say summation of forces in xi plus summation of forces in yj plus summation of forces in zk has to be 0, which means this is 0, this is 0, and this is 0. Remember, all of the three are the same representation. What is our problem here? Express each one of the forces in Cartesian notation. How? Multiply the magnitude by the unit vector. How to calculate the unit vector? Calculating the position vector and subtracting and dividing the position vector by the magnitude of the position vector. So let's start with AB. AB is this one here. And let's start with the position vector AB. What is the position vector for AB from here to here? Well, for that vector I have to come here. And I have to go here. And I have to come here, parallel to the axis. Well, let's do that. The position vector AB goes from A to B, and in X is this distance, which is 10 I, and in Y is from here to here, which is negative because this is the positive direction and I'm going back. Negative 15J, and in K is coming down also, which is negative 30K. And you can do that if you want subtracting coordinates also. I'm just doing it differently so you can practice both. This is the position vector AB, but I'm not interested in this case of position vector AB. I'm interested in what? In the unit vector for AB. So what I'm going to do is I'm going to divide this by the magnitude of AB, which is just 10 squared plus 15 squared plus 30 squared. But wait a second. Are we interested in that, or we're interested in the force? No, we're interested in the force AB. Well, then I'm going to multiply the magnitude of the force AB times this, which basically is going to be only this multiplied by the force AB. Period. And when you solve this is going to be the force AB as a vector. Is going to be, this is 35, 10 divided by 35 is 27. So 27 I minus 37 J minus 67 K multiplied by FAB. And we have one equation. Now, done with that. Let's go now with the second one, the force AC, this one here. For the force AC, same thing. I have to come here, go there, and then go back here. That's what we have to do. Which, basically what it's telling us for the force, for the position vector AC, is that in X is from here to here is negative 15 I, in Y is from here to here, which is negative 10 J, and from K is from here to here, which is negative 30 K. And exactly as in this case, I'm not interested in the position vector, but in the unit vector. That means that I have to divide it by the magnitude, which is the same magnitude than in this one, by the way. And because I'm not interested in this also, I have to multiply this by the magnitude of AC, which means multiply this by the magnitude of AC, which means that we're going to have the force AC as a vector, I mean not magnitude vector, that's going to be equal to negative 37 force AC, negative 27 I, 27 force ACJ, negative 67 force ACK. And that would be my second equation. Here, you can put this also in. That's the correct way of doing it. And the last one, or not the last one, but one of the last ones, next to last, the force, I can do the force AE. The force AE directly is going to be equal to force AE acting in K, because it's going only as a vector in that direction. And the other one is this one. And for that one, then I'm going to come same thing here and here. That cable is completely over the YZ plane. So there's no coordinates in the X direction, in the Y direction. So then what I'm going to do in the X direction. So what I'm going to do here is, this is going to be for the force, or let's say the position vector AD. Same thing, position vector AD. Position vector AD is going to be equal to this distance, 12.5 J, and this distance is negative 30 K. And what do I do with this? I am interested in the position vector, the unit vector, so I divide this by the square root of 12.5 squared plus 30 squared. And because I'm interested in the force, what I'm going to do is then I'm going to get this value that I got before, and then I'm going to multiply this value by the magnitude of the force, which is 1300. And that's going to give me the force AD. And the force AD is going to be, let me see, 500 J minus 1200 K. So I have 1, 2, 3, and 4. Once I have those forces, 1, 2, 3, and 4, I'm sorry about that. I didn't realize that the paper was tilted. So once I have these 1, 2, 3, and 4 equations, what I have to do is put all the equations together. And if I put the first one is, let's put this one, 27 FAB I minus 37 FAB J minus 67 FAB K. That's the force AB. The force AC is negative 37 force ACI, negative 27 force ACJ, negative 67 force ACK, and then we have the force AD, and the force AD here is 0, 500 J, negative 1200 K. And then I have also this force, force AEK, 0, 0 K. Summation, all the forces has to be 0, 0, 0. And as you can see, working with these two, basically I'm going to have this equation, 27 force AB minus 37 force AC equals 0. The second one is negative 37 force AB negative 27 force AC plus 500 equals 0. And then this, the last equation is negative 67 force AB negative 67 force AC minus 1200 plus FAE equals 0. I have 1, 2, and 3 unknowns. I have 1, 2, and 3 equations. We have a perfectly defined system of equations, which means we can solve this problem. If you want to solve it by hand, work with these two. And you can multiply the top equation by 1.5 if you want to, because by multiplying the top equation by 1.5, this becomes 3/7 and cancel with this one. So this is going to be 4.5 negative plus 2 is 6.5. So basically it's going to be 500 multiplied by 7 divided by 6.5. And at the end you're going to have the force AC to be equal to 538.46 Newton, and the force AB equal to 807.69 Newton, and the force AE, because once you have the force AC you can plug it back here, calculate force AB, and once you have AB and AC you can plug it into here and calculate AE. It's 2,353.84 Newton. And these are the three forces that the problem was asking us to calculate. Well, this is the last problem for today. I hope that you take advantage of this that I'm doing for you guys. Don't just limit yourself to look at the problems and say, oh, I understand what he's doing. No. Copy the problems again. Try you to solve the problem. And if you get stuck, you go back and you review whatever I'm doing. And don't limit yourself only to the homeworks and to this problem. Go to the book or books. Try to find more challenging problems even than the ones that I'm showing you right now. Well, this is it for today. I'm going to try next class I'm going to try to record something more about chapter 4 now. I think we're done for chapter 2 and 3. So chapter 4, I'm going to try to start working with chapter 4 and 5, which is the content for the test. I'll see you in my next problem session, guys, and in class.